Hello friends, welcome to our YouTube channel, Gajpal A-Learning. In today's video we are going to see about atomic weight, molecular weight, equivalent weight, and primary and secondary pharmaceutical standards. So let's get started. First is atomic weight. Atomic weight, also known as atomic mass or relative atomic mass, is a measure of the mass of an atom of a chemical element relative to the mass of an atom of carbon-12, C12, which is assigned a mass of exactly 12 atomic mass units, AMU. Atomic weight takes into account the abundance of isotopes of an element and their respective masses. Atoms of a given element can have different numbers of neutrons in their nuclei, leading to the existence of isotopes. These isotopes have the same number of protons, which defines the element, but different numbers of neutrons. Since the atomic mass is influenced by the presence of these isotopes, the atomic weight is an average of the masses of all the naturally occurring isotopes of an element, weighted by their relative abundances. For example, carbon has two stable isotopes, carbon-12 and carbon-13. The atomic weight of carbon is the weighted average of the masses of these isotopes, taking into account their natural abundance. Carbon-12 is more abundant, so it contributes more to the overall atomic weight of carbon. Atomic weight is expressed in atomic mass units, AMU, or unified atomic mass units, U. It's important to note that atomic weight is a dimensionless quantity, as it's a ratio of the mass of an atom to the mass of a reference atom. The atomic weight of an element is typically found on the periodic table of elements. It's important for various chemical calculations, especially when dealing with stoichiometry, which involves the quantitative relationships between substances in chemical reactions. We should keep in mind that atomic weights may appear as decimal values on the periodic table due to the presence of isotopes with slightly different masses. Second is molecular weight. Molecular weight, also known as molecular mass or molar mass, is the sum of the atomic weights of all the atoms in a molecule. It's a measure of the mass of a molecule relative to the atomic mass unit, AMU, and is expressed in atomic mass units or grams per mole, G per mole. Let's take the example of sodium hydroxide, NO. Sodium, Na, has an atomic weight of approximately 22.99 AMU. Oxygen, O, has an atomic weight of approximately 4 pmu. Hydrogen, H, has an atomic weight of approximately 101 AMU. The molecular formula of sodium hydroxide is No, which indicates that there is one sodium atom, Na, one oxygen atom, O, and one hydrogen atom, H, in each molecule. Now, let's calculate the molecular weight of NaOH. Molecular weight of NaOH equals atomic weight of Na plus atomic weight of O plus atomic weight of H. Approximately equals 22.99 atomic mass units plus 16.00 atomic mass units plus 1.01 atomic mass units. Approximately equals 40.00 atomic mass units. So, the molecular weight of sodium hydroxide, NaOH, is approximately 40.00 atomic mass units. In terms of grams per mole, gram per mole, we can convert the molecular weight from atomic mass units using the molar mass constant. 1 gram per mole approximately equals 1 atomic mass unit. Therefore, the molecular weight of NaOH is also approximately 40.00 grams per mole. Molecular weight is crucial in various areas of chemistry, including stoichiometry, where it's used to calculate the amounts of substances involved in chemical reactions. It's also important in fields like analytical chemistry, where it helps in determining concentrations of solutions and identifying unknown compounds. Third is equivalent weight. Equivalent weight is a concept used in chemistry to quantify the reactive capacity or the amount of a substance that can either gain or lose a certain number of electrons or react with a certain number of moles of another substance. It's particularly useful for understanding the stoichiometry of chemical reactions, especially in acid-base and redox reactions. Equivalent weight for acid. For acids, the equivalent weight is the amount of the acid that can donate 1 mole of protons, H icons, in a reaction. It's related to the molecular weight of the acid and its acidic functionality. For monoprotic acids, those that donate 1 proton per molecule, the equivalent weight is the same as the molar mass. For polyprotic acids, those that can donate multiple protons, the equivalent weight is calculated based on the number of protons they can donate. For example, consider hydrochloric acid, HCl, which is a monoprotic acid. Its molecular weight is approximately 36.46 grams per mole. Since it donates 1 proton per molecule, its equivalent weight is also 36.46 grams per mole. And for H2SO4 its molecular weight is 98 and it is capable of donating 2 hydrogen, so 98 halves gives the equivalent weight of 49. Equivalent weight for base. For bases, the equivalent weight is the amount of the base that can accept 1 mole of protons, H icons, in a reaction. It's related to the molecular weight of the base and its basic functionality. Bases can be monobasic, accept 1 proton, or polybasic, accept multiple protons, and the equivalent weight is calculated accordingly. Take sodium hydroxide, NaOH, as an example. It's a monobasic base with a molecular weight of approximately 40.00 grams per mole. Since it can accept 1 proton per molecule, its equivalent weight is 40.00 grams per mole. Equivalent weight for salt. For salts, the equivalent weight is related to the ions present in the salt and their charges. It's the mass of the salt that can either produce or react with 1 mole of a particular ion. Consider sodium chloride, NaCl. It dissociates into sodium ions, Na, and chloride ions, Cl, in water. The equivalent weight for sodium chloride is the mass that would provide a react with 1 mole of sodium ions or 1 mole of chloride ions. Since sodium chloride provides 1 mole of sodium ions and 1 mole of chloride ions for every mole of salt, its equivalent weight is half its molecular weight. Equivalent weight for precipitation reactions, P. In the context of precipitation reactions, equivalent weight refers to the amount of a substance that can either produce or react with 1 mole of an insoluble product. This concept is particularly important in double replacement reactions where 2 soluble ionic compounds react to form an insoluble precipitate. Let's use the example of the reaction between silver nitrate, AgNO3, and sodium chloride, NaCl, to produce silver chloride, AgCl, precipitate. AgNO plus NaCl right pointing arrow, AgCl down pointing arrow plus NaNO3. In this reaction, both silver nitrate and sodium chloride are soluble compounds, but when they react, they produce insoluble silver chloride precipitate. Since 1 mole of silver chloride precipitate is produced per mole of sodium chloride, the equivalent weight of sodium chloride is its molar mass. Similarly, the equivalent weight of silver nitrate is its molar mass, as 1 mole of silver nitrate produces 1 mole of silver chloride precipitate. Note: equivalent weight for acid is the amount of acid that donates 1 mole of protons, H icons. Equivalent weight for base is the amount of base that accepts 1 mole of protons, H icons. Equivalent weight for salt is the half the molecular weight of a salt, as it provides or reacts with 1 mole of a particular ion. And equivalent weight for precipitation reactions, P, is the molar mass of a substance that produces or reacts with 1 mole of an insoluble precipitate. Next topic is primary and secondary standard in pharmaceutical analysis. In pharmaceutical analysis, primary and secondary standards are crucial concepts used to ensure the accuracy and reliability of analytical measurements, especially in the context of quantitative analysis. These standards are used as reference materials to calibrate instruments, validate methods, and determine the concentration of unknown substances. Let's delve into the details of primary and secondary standards. First, primary standards. Primary standards are highly pure compounds that have a well-defined composition and are used as a reference for directly calibrating analytical instruments or methods. These standards possess several key characteristics. A. High purity. Primary standards must be of extremely high purity, often exceeding 99.9%, to minimize the potential for impurities affecting the accuracy of the measurement. B. Stability. They should be stable under normal storage conditions, ensuring that their composition remains unchanged over time. C. Solubility. Primary standards should be readily soluble in common solvents, which aids in their accurate preparation and measurement. D. Non-hygroscopic. They should not readily absorb moisture from the environment, as this could lead to inaccurate weighing and concentration determination. A. Low reactivity. Primary standards should have low reactivity with common laboratory materials and reagents to prevent any unintended reactions during handling and storage. F. Traceability. The purity of primary standards should be traceable to a recognized reference organization, such as the International System of Units, C, or a National Metrology Institute. Examples of primary standards: potassium dichromate K2Cr2O7, used for the calibration of UV-vis spectrophotometers by measuring its absorbance at a specific wavelength. Sodium carbonate Na2CO3, used to standardize solutions of acids in acid-base titrations. Primary reference standards, PRS, these are standards provided by official pharmacopoeias, e.g., USP, APE, and are used to ensure the accuracy of drug assays and other pharmaceutical tests. Secondary standards. Secondary standards, also known as working standards or reference standards, are solutions or compounds prepared from primary standards. These standards are used for routine calibration of instruments and validation of methods. Secondary standards share some characteristics with primary standards, but they don't require the same level of purity or traceability. Instead, their preparation involves accurately weighing a known amount of a primary standard, dissolving it in a suitable solvent, and diluting to a known volume to create a solution of known concentration. Characteristics of secondary standards. A. Accuracy. While not as rigorously pure as primary standards, secondary standards should still be accurately characterized to ensure reliable calibration. B. Traceability. Although they don't require the same level of traceability as primary standards, their preparation and handling should still follow documented procedures to maintain consistency. C. Usability. Secondary standards should be stable over a reasonable period, allowing for multiple calibrations and measurements. Examples of secondary standards. A. Standard solutions, prepared by diluting a primary standard to a known concentration, often used in analytical techniques like chromatography, titrations, and spectrophotometry. B. Internal standards. In analytical methods like chromatography, an internal standard of known concentration is added to both standards and samples to account for variations in sample preparation and analysis. In summary, primary standards serve as the ultimate reference for accuracy and purity, while secondary standards are practical tools for routine calibration and validation. The proper use of these standards ensures the reliability and accuracy of pharmaceutical analyses, which is critical for drug quality control, research, and development. Thanks for watching this video. In the next video we will see about some preparation and standardization of some standard solutions. Thank you.